Welcome to the Math Bulb. I'm Dr. Rachel Traylor, lead researcher at the Math Citadel. Math Bulbs are short explorations of interesting topics, surprising connections, and strange questions. So, for example, what does MMA fighting have to do with pure math? So, let's say that we have two fighters here. So we've got this fighter here and another fighter next to him. How do we pair them up? Well, we put them in weight classes, right? These are two distinct fighters. They have different weights, but we choose a weight class to put them in. So if the guy on the left is, say, 117 pounds, and the guy on the right is 120 pounds, then we consider them to be in the same weight class, which means that we can match them up to fight. So we consider these two fighters equivalent as far as fighting is concerned, even though they're two distinct fighters. Okay, so what have we actually done with these weight classes? We've essentially taken the entire set of possible fighters and partitioned them by weight. So, moving on, what exactly is a partition mathematically? So let's say we have a set and it's got some stuff in it, and we can actually partition them just like the weight into, say, 3 different sets here. So this is simply a family of non-empty subsets, and these AIs just are indexed, that are mutually disjoint and whose union is A. That's all a partition is. So it's taking all of the existing items and simply just drawing lines to separate them out. So let's get a little bit more terminology here, and let's quickly talk about relations. So a relation on that set A, and this is probably the most elegant definition I've ever seen, any statement which is either true or false for each ordered pair of elements x, y, and a. So that means like equals, greater than, less than, those are all relations. It's ways to compare two elements. Now, we do need to talk about some special kinds of relations. And these are equivalence relations. So we write that x tilde y, and that's denoted x is equivalent to y. And that's defined as a relation on a set A which has 3 things. 1, it's reflexive. So everything has to be related to itself. Let's avoid some existential crises here. 2, it's symmetric. So if x is related to y, then y has to be related to x. Equivalent. So, and transitive. So if x is equivalent to y and y is equivalent to z, that means x is equivalent to z. Now here's the thing to note here. I told you that our examples of relations were equals, greater than, less than, greater than, equal to, just a few examples. Now, which of those things are equivalence relations? Well, they're all reflexive. Actually, less than kind of fails that, doesn't it? Kind of fails reflexive, and it fails the symmetric. So, not all relations are equivalence relations. All equivalence relations are relations. Equivalence relations are a special kind of relation. Equals is still there. So now let's take a mathematical example of an equivalence relation that's a little bit more interesting than just equals. So I did a post, and you'll see the link below, on what it means to take the integer's mod sum number. So let's take z3 for example. So z3 is all the integers mod 3. In other words, what is the remainder when you divide any integer by 3? So z3 is simply equal to 0, 1, or 2. When you divide a number by 3, those are the only possible remainders you can get. We can actually notice that there's a little bit more to z3 than just numbers. In fact, they're boxes. So let's take a look at this animation here. So if I make these boxes, watch what happens when I take the numbers 0 through 5. So 0 divided by 3 is 0 with the remainder of 0. 1 and 2, right? Obviously they don't really divide 3 evenly. But let's move to 3, 4, and 5. So 3 divides itself, right? So there's no remainder left, which means it goes in the box of 0. 4 divided by 3 is simply 1 with a remainder of 1, so it goes in that box with 1. 5, same thing. Now what do we notice? Just like those fighters, we see that under mod 3, which is an equivalence relation, 0 and 3 are equivalent. 1 and 4 are equivalent. 2 and 5 are equivalent. 9, which box would 9 go in? Well, 9 is divided evenly by 3 into 3, so 9 would simply go in this box right here. So you kind of get the idea. We're taking all of the integers and partitioning them into these 3 boxes. So equivalence relations are just a way of partitioning anything, right? We used the math example of integers. We used the real example of fighters. So in this case, the equivalence relation is probably not an easy thing to just write out. It's just weight classes, but it's still a partition, and there's still an equivalence relation. If 2 people belong to the same weight class, they are considered equivalent. So what did we learn? Equivalence relations are just a formal mapping that partitions a set of anything you like. Integers, fighters, currency, and many other things you can think of. So once you've used an equivalence relation to partition a set, those partitions now are called equivalence classes. Why do we care? So the nice thing about equivalence classes is that we can simply study the classes themselves rather than the individual elements, which cuts down on redundant comparisons. If we didn't have weight classes, I would have to look at each individual fighter, compare their individual weights, and see if they match up and are equivalent in the sense that they can fight each other. We don't need that. With weight classes, if they're in the same weight class, pair them up however you like, right? They're equivalent, so we don't have to worry about it anymore. Basically, that's what mathematicians do. We want to step back and take an aerial view and see how many different things there really are. So if we partition the integers in, say, like by mod 3, because we're interested in that, even binary, right? That's probably got more practical implications. That's just partitioning the integers by mod 2. Well, you can basically just study 0 and 1 now as equivalence classes. So now there really aren't infinitely many different integers. There's just 2 equivalence classes we have to worry about and their interactions. Thanks for tuning in to the Math Bulbs through the Math Citadel. Be sure to check out our website for more videos, posts, commentary, and original research papers. Comment below on topics that interest you, or feel free to contact us through the website or on Twitter at Math Citadel. So until next time. Math bulbs are short explorations of, can we stop? I'm clearly looking at something.
Yeah.
Do a clap. Totally lost my train of thought. It's fine. No, don't stop it. We'll just edit it out. What was I gonna say here? I don't want to look at each individual M&M. Yeah, they have all different colors, but they're all still M&Ms as a food example. Clearly that means I'm hungry. Still lost my train of thought, but it's okay.